Hello again. Now we're just going to make a start on the final video, and this one's going to be looking at supervised classification. I think we talked about this earlier on. Just some work I did for Neathport Talbot County Council, trying to quantify changes in urban cover by ward between 1986 and 2018-2019. This is associated with some green infrastructure works they're doing and trying to get an idea of how urban extent has changed through time and how this has affected the distribution and access to green space for people on a ward by ward basis. So this could be done manually through visual mapping pixels, basically. So you could download some remotely sensed data of the areas, or if you had aerial data available, and you could do it by hand. You could go through and map out the areas that were urban, so non-green, so grey infrastructure, and then collate some of these by hand. It would be quite a time-consuming process. Neathport Talbot is quite big, so it would take you a little while, but I mean, it certainly could be done. But what we're going to do, we're going to use a different approach. We're going to use a machine learning approach. We're going to use a supervised classification approach, and we're going to do this by taking attributes associated with pixels that represent urban areas and pixels associated with non-urban areas, and train a classifier, a machine learning algorithm, to be able to tell the difference between the two. So use those attributes to allow an algorithm to determine between the two classes, which are urban or not. So in supervised classification, we usually have some kind of prior knowledge of the land cover type, so we know what's there. This is versus unsupervised classification, where you don't perhaps know what's there. So usually this data is attained through field work or some reference spatial data, or you can interpret high resolution imagery. So in this example, we will be using training data sets that I've collated from inspection of satellite data. So the general workflow for supervised classification follows this kind of 5-step procedure. So you generate the sample sites based on our prior knowledge, and then you extract the SAL values from the satellite data or the remotely sensed data. So it might be visual data, might be near infrared data, might be interpreted data, so like NDVI, which we will use in this classification, or it could be other land classification data as well. So you could use MODIS land classification data perhaps to help. And then we'll train a classifier using these training samples. And we're going to use a random forest classifier today. This is just a machine learning algorithm which is based on decision trees and uses an n number of decision trees to take a random sample of the parameters and run separately, and then vote by majority at the end to come to an agreement on the output classification. So these kind of classifiers should be shown to be more accurate than simple decision trees by the majority voting system, basically. So we'll be using inbuilt random forest algorithms in Google Earth Engine, but it's also worth knowing and being aware of that GE now can also accept model outputs from TensorFlow. TensorFlow is open source software library supported by Google, Google Brains team, and Google AI. And it provides access to a number of machine learning and deep learning algorithms. So some of the cutting edge kind of image analysis and object detection and classification works is being done in this kind of format. So deep learning is a particular kind of machine learning algorithm, basically that you've probably heard of somewhere else, many places. But there's some examples here in the text that you can go and have a look at, and there's an example script here in Python. So you do have to actually interact with TensorFlow through Python. So if you're not familiar with Python, you'd have to get familiar with that first. And there's a good video here summarising how the two can interact with Google Earth Engine. Essentially, you can take model outputs from TensorFlow and drop them back into Google Earth Engine to allow you to classify imagery. But anyway, so we're going to be using the native classifiers present in Google Earth Engine, and you can find more details of there on the Google Earth Engine developers page. So the classifier is available in Google Earth Engine include cart, random forest, naive Bayes, and SVM, so support vector matrices. So today we'll be using random forest, which is a classic kind of machine learning algorithm, and it's been shown to be really effective. So it's an approach that fits a number of decision trees on various subsamples of the data set and uses the average to improve the predictive accuracy and control over fitting. There's important kind of tuning parameters associated with random forest. So I mean, this is just a quick kind of toy analysis we're doing here today. If you are going to use it for any research, and especially in Earth Engine, I'd recommend you look into the function and look at the tuning parameters. There's more information on random forest here. This is the Fortran coded example, but the background to the maths is in here. It's good to understand some of the technical terms before you apply it in anger. So this is kind of simplified representation of what happens in a random forest. So like I said, we're going to use some pre-selected training polygons that I've selected and use that to classify some Landsat imagery from 1986 and 2019, and then sum the values up of classified urban cover by ward, and then produce some visual outputs to allow interpretation. So this is just a general workflow for undertaking the analysis and providing some interpretation for a client or supervisor. So if we take all this code out, and I'm sorry, but there is a lot of code for this. Most of it's associated with the geometry for the training polygons, and it's just that's because that's the easiest way to transfer them between scripts is to code them longhand, as it were. So if we paste this in, and I'll talk you through what we're doing in the script. So the first part of the script is introducing this table object. The first line, sorry, is incorrect. We don't need that. Creating this variable table, which is a feature collection, and this is again using the wards at MPT, and the geometry associated with these. And then there's multi-polygon geometry. These are the training data sets, so geometry and geometry 2. And they are associated with the polygons for urban land areas and non-urban land areas, respectively. So once we've got these in, then I'm creating a feature. I'm changing them into a feature collection. In line 371. And assigning geometry to the class 0 of other, so non-urban, and geometry with a class 1, which is urban, and then printing this to the console. Changing these features into a feature collection here, which is probably not needed. Printing it out again, and then adding the layer. And you can change this ROI is incorrect to map center object habs, and add in layer habs to the map. And then we just got a couple of functions in here, which functions to calculate the normalized difference vegetation index for this is the Landsat 8 and this is the Landsat 4 to 7. Basically the bands needed to calculate NDVI change between Landsat 7 and 8, so we need different bands listed. And then in lines 390 we are assigning a variable L5 call image collection of Landsat data. So this is the Landsat surface reflectance data, tier 1 surface reflectance, and we're filtering it. We want to filter it by cloud cover, so we don't want cloudy images, we want as less cloud as possible, so we've gone with a 5% cutoff. Unfortunately it's quite cloudy in Wales, so if we go with 0 we tend to get no results. And then we're filtering it by the bounds, by table. So this is our table variable for NPT. So we're telling them we just want it to return the region of that is found within table, and we want the image between 1986 and 1988. And once we got that data, then we want to map this function to it. So this function NDVII, but map just means apply a function across the imagery. So what is going to happen is on the Google Earth servers, they're going to filter the data, available image collection, by these parameters, and then once it has the results of that, they're going to map NDVI over it and add that layer to the image. Then we're going to merge this collection and print the collection to the console. This line 400 to 402 here is just a bit of commented out code. It's useful to run with the parameters around date to figure out how many images you've got in a time period. So we won't do that in this run through, but it's something you might like to play with if you're changing the area of interest. And in line 404 to 407, we're merging the returned images into a single mosaic image for our area of interest. So we're using this function median, and this takes the median pixel value, which is often used in more tense applications as the mean, and the min and the max tend to be associated with cloud usually. So the median is a more reliable way of getting a representative or good image. So then I'm just defining some visible parameters for the visual spectrum, so we can add the Landsat median image to the background and have a look at it. So this is 1986, 1988. Then our points, we're reassigning points here with the class for the habitats that we defined earlier on. So this is basically telling the this line is wrong. This is defining, creating variable points as associated with the feature collection habs and changing the class, or telling which class they are. Points. We're going to use these points basically. You can't use the polygons to sample. You need points to train the data set, and we're creating points from our polygons here and giving them a class of 0, 1, which we defined earlier on. We're adding these points to the map, and then we're selecting the bands we want to train our data set, so band 2, 3, 4, 5, 6, 7 and NDVI, and merging these into an image, single object image here. This is the training data function, so we're sampling the regions at the points, and the properties we want to sample is class, the properties associated with a class is the training data, and the scale is 30 because the Landsat data is again 30 meter pixel resolution. And then we're training our classifier based on this data, and then we can classify our image, the input imagery, and update the mask to basically remove the things that are below a threshold of 0.5. So in this instance we're just retaining the urban areas. And then just some methods of calculating the accuracy of your model. So you can create a confusion matrix, which is basically the correctly identified classes from the known areas versus the incorrectly identified classes from the training data, and these give you an idea of accuracy of the approach, and it just gives you a figure out between 0 and 1, basically giving you a percentage of accuracy. And then here we're doing is converting this data to area, as we did with the forest change data sets earlier on, and then summing the pixels, so again using reduce regions and the sum function, which you remember from the forest data, and then printing this to the console. Outputting it as an asset, don't need to run this if you don't want to, but also creating a chart. And then visualizing it as a map, as we did with the forest loss data for the wards in East Port Talbot. And then we're doing the same thing again, but for a data set from 2018 to 2020. So, and this is using the Landsat 8 data, and it's worth noting now we've changed the NDVI calculation to the NDVI as opposed to NDVII, as this is using Landsat 8 data and the bands are slightly different. The code below that is essentially the same though. So let's run this code eventually. Finally, hopefully it'll work. Yeah, so now you can see the code running. If I open the map back up, you see things starting to appear in. Hopefully this is appearing in your window also. You see the tasks, here are the outputs. So these are feature collections or shapefiles containing the urban cover statistics for 2019 and 1986. So we could run that and that would output as an asset to here if you wanted. Let's go back to the console. You can see we've printed out feature collections, image collections. These are our accuracy statistics, or kappa, and conversion matrix accuracy. So you can see that accuracy is 98-99% for our training data. And here are our graphs. So this is ward area in 1986, and you can see ward area in 2019. So worth noting the scales are quite different here. So 30 million at the top end there, and 14 million here at the top end. But you can see there's some significant differences there. Amalgam is particularly interesting. You can see this. If you look at 2019 versus 1986, obviously amalgam went underneath significant development over this period of time. So what other outputs have we created here? You can see the maps. If we look at the layers here, you've got, this is our training data in points, default display, points again. This is the Landsat 1986 data. So if we take all this off, this is the actual Landsat data from 1986. And this is our urban classification by ward. In 1986. If we turn this Landsat background off. So this is, remember, the sum data by ward, giving you a total meter squared per ward, and then displayed. So we can see quite a big difference between 1986 and 2019. Okay, I'm going to finish that video there, I think. So obviously a lot of code there to go through. But I would encourage you to have a play with it, break it, and try and fix it, and then perhaps try and apply it to other applications you might find interesting. I put a couple of thoughts or suggestions in the course notes, but yeah, so have a go at those, or play with this data, or play with the examples. There's lots of examples in the code scripts here, and in the data sets and demos. There's some really great information in here. So yeah, have a play around, and yeah, I hope that was useful and interesting. Thank you very much.